Hello, calculus students. Today is section 2.1. This is a asynchronous day for learning. I've got a warm up here. If you want to press pause, try the warm up, and then hit play when you're done and check your answer. Okay, so we've got the Algebra One warm up. Write the equation of a line that goes through the 2 points. Well, to do that, I need to know the slope. And to find the slope, we're going to do rise over run, which is really just the change in y's over change in x's. We are going to be referring to slope all day today and basically all year. That's the basis of of calculus is slope. So what if I find the slope right here? I know what my y2 is. I'm going to subtract y1 and subtract x2 minus x1. Subtraction of a negative. We end up with 11. And then I want to write the equation of the line that goes through that. We're going to be doing this today, except for we're going to call it a tangent line. I am going to strongly recommend you use the point slope formula. You will definitely benefit from using that as we go along here. So what do we know? We know the slope is 11. I know that y1 is -2. And I know that x1 is 3. Now, technically, you could stop here, but we also want to do the distributive property, distribute the 11, and then subtract 2. And here's the equation of the line given 2 points and finding the slope. All right, so here are our learning targets for today. We're going to introduce something called rates of change. You've heard of that in Algebra 1. The rate of change is just the slope, but now we're going to tie it to this new definition and this new concept called the derivative. We're going to work with derivatives for probably the next 2 months, and you are going to get very well acquainted with the derivative. So we're going to introduce how change can occur at an instant, and then find average versus instantaneous rates of change, defining the derivative of a function using derivative notation and limit notation, and then we'll be doing some estimating as we go along. So I would like you to write this part here. It's quite a bit, so buckle up. We're going to kind of introduce this idea of what is a derivative and how do we find it and how do we think of it graphically. We're going to start off with things that you know. So let's talk about this quick before you kind of start writing some things. Let's take a look at what we have. What if I have 2 points? What if I have a point here at C and I have another random point at X? Well, we kind of just did that in the warm-up. We had 2 points and we found the slope, and then we found the equation of that line, right? And this is just a fancy way to write slope. So the slope of a secant line, remember the word secant in geometry was referring to a circle that went through the circle and touched it at 2 points. Well, it's the same thing with the function. So my secant line touches our function f of x at 2 points. When c is the input, f of c is the output. When x is the input, f of x is the output. Well, I could do the slope equation. I could take my change in y's. Let's do y2 minus y1. So here's slope. F of x minus f of c. That's my change in y's over the change in x's, x minus c. You can kind of see that here. I could label x1, y1, x2, y2 the same way we did before. But notice when we say slope, all it is the average rate of change. A lot of times you'll see teachers and students abbreviate it as Iroc, average rate of change. And that's just the change over 2 points. Think of regular slope from Algebra 1. So why is that important? Well, we can find the slope given 2 points. But what happens now if I take this point? What if I take this point for x and now I change it and it moves closer? Now all of a sudden the slope is changing, right? You can physically see the slope of that line change. So I could get closer even still. So what happens if I move closer and closer and closer? You can see this slope is changing. It's still a secant line because it goes through the spot, through the function at 2 points. But what if x moves closer and closer and closer to c, so it's the closest it could possibly be, which basically says, what if x and c are the same thing? Now, all of a sudden, look at what happens to our line. It no longer is a secant line, but it is a tangent line. And remember, a tangent in geometry is when you touch the circle at one point. Well, how can I take the slope formula if x and c are the same thing? Doesn't that give me 0 in the denominator? We can't have that. That's an undefined term or an indeterminate form, as we saw earlier with limits. So what about, how do I find the slope of a tangent line? Well, the only way to do that is to use the idea of a limit. We know that as I approach c from the left and c from the right, it doesn't matter what the point is, but we can find the limit as we get really, really close to a value, which in this case actually ends up being c. So what if I take the same idea? Notice this is the same slope formula, but I just say x is going to get closer and closer to c, and we saw that on the graph. As x gets closer and closer to c, the limit is going to make it so it actually gets close to or on top of perfectly matched with c. Well, okay. How do we do that? The only way this is going to work is if the limit truly exists. And if the limit exists, then we can find what's called the derivative, which has a fancy notation. See this little tick mark here? The slope is actually the same as the derivative, and this is called f prime. That's our notation for derivative. We're going to get into that quite a bit. You'll see that in the examples we work through here today. But a couple things to think of. Okay, well, what is this new notation if I use the limit? That's the slope at exactly 1 point. How do we find the slope if it's at 1 point? We need 2 points to find slope from algebra. Calculus, we can do it with 1 with the concept of the limit. This is known as Iroc, or instantaneous rate of change. I believe our textbook commonly refers to it just as rate of change, and they'll give you a single point. But if you see the word instantaneous rate of change, that's our idea of this is the derivative. So we are going to make a contextual connection to this, and think of this as if you took 2 points and you found your average rate of change, that would give you your miles per hour, right, over the distance of like a trip driven. What was your average rate of change from the start to end? Well, as you drive, you're given feedback instantly on your car, and you're actually referred to your speed at a specific moment in time. You can find that, and that's just the derivative, which is also known as velocity. So we're going to make a contextual connection to that. And we're still going to make another connection to the equation of a tangent line. So think of the warm-up we just did. You have the equation of a tangent line. What do you need? You need a point and you need a slope. Well, what is the slope? Slope is the derivative, f prime of c, and then let's look at our connection here. By the way, you can pause this video at any moment and record the notes. If I go too fast, pause it, rewind it. I just don't want to have a video that's 35 minutes long. So, all right, what do we know? Well, algebra one way was point and slope. Here's my point, x1, y1. Here's my slope. What is the calculus way? It's the exact same thing. I'm going to have, y minus whatever y1 is. That's not cool. Sorry. Okay. Here's what I know. My slope is the derivative at a point C. Well, we had the notation that f prime, that little tick mark is prime, at the point C. Well, what is that? C is my input, and as C goes into the function, regular f of C comes out. So this is another way to write the equation of the tangent line. And it's the exact same concept. There's my slope, and then my point was C comma f of C. It's just function notation, and that's, you can see where the x value went in and the y value. And it's the exact same thing as what we did in the warm-up. So we'll get used to how that works. All right, well, let's take a look at this example. So find the equation of a tangent line. We're going to do part A first. Find the equation of the tangent line of the graph f of x equals x squared at the point. Okay, what do they give us? They give us a point, but we don't have the derivative. We don't have the slope. So that's what part A is asking first, is I need to find the slope. And you're going to notice one of the things I recommend here, by the way, again, pause it if you need to. You're going to notice that I really write out what we're working with before I decide to plug in any numbers. I think it's important to just look at this every time and think, okay, well, what is this? You need to understand what f of c means. F of c is the function. It's x squared. So we're going to put an x squared right here. X is the input, so I don't have to put anything there. But what is f of c? C is the point of interest, right? C is our x value. So in this problem, c is equal to -2. And then I have to figure out what is f of c as well, or f of -2. Okay, so that's understanding the setup. Now let's actually work through it. What I'm going to do is say, you know what, c is no longer the c. That's our input. That's the value that we're looking to approach, which is -2. And you can see here's the c as well. I should have highlighted that in green. All right, so f of x goes into my function. Here's f of x. It's x squared. And then I'm going to subtract whatever f of c is. F of c at -2. And then we're going to subtract or divide that by x minus whatever c is. Well, c is -2. Notice the subtraction of the negative. Well, that just means I have to find one piece of information. I have to figure out what is f of -2. You don't need to show any work for this, but I think of this as side work. If the function is x squared and -2 goes into the equation, -2 squared ends up being +4. So that portion is +4. And now I have a limit, just like what we got done with in the last unit. The bottom is going to turn into an x plus 2. So now we actually just have to evaluate this limit. Notice I can't plug in -2. If I do substitution, I get the 0 over 0, which means we have to do some type of algebraic trick, which we learned factoring is usually the best thing to look at. The top numerator is a difference of squares. X squared minus 4 is really x minus 2, x plus 2. And then we're going to reduce out the factor of x squareds. So what's left over is the limit as x goes to -2 of x minus 2. Now, I do want to make a strong connection here for you. What did we just find? We found the equation. This is the derivative for any x. Right here, x minus 2 is the derivative. You know what? Let's scratch that right now. We're not ready for that yet. Sorry. What we can do though is now we can plug in -2. So I'm going to plug -2 into x, -2. -2 minus 2 is -2, -4. So what did we just find? We found the derivative f prime of -2 is equal to -4. That's my slope. We just found the slope of the tangent line at that point. So that's what part A is asking. Part B is actually much friendlier and way less work. All right, part B, I have to use the result from part A to find the equation of the tangent line at the point -2, 4. So what do I know? -2, 4, that's my point. That's x1, y1. And the slope is -4. We just found that. So I'm going to take my equation and I'm just setting up the equation of the tangent line that we just talked about on the last page. I could have wrote y minus y1 equals m times x minus x1, but what do we know? We know that f of -2 is the output. We just actually found that right here in the first part. That's equal to -4. And then we've got the input, which is at -2. And then the last piece is the slope. What is f prime? Notice that little tick mark. That's really important. That's called prime at -4. So we're going to simplify. I know what f of -2 is. I know what the slope is. And I know that when the x is -2, this is going to make it +2. And you could technically stop here, but you could also distribute and then add the 4 over. And we end up with the equation of the tangent line. So let's check that with a graph, just so you know what we're doing. I'm going to pause it and come back with a graph. All right, let's check this with a graph. And you'll notice what I did. I took our original function x squared, it's just a regular parabola. I put the point, -2, 4, because that's our point of interest. And if I wanted to find the slope of the tangent line at this point, that's the work that we just did. Our answer was -4x minus 4. So watch when I activate that. Notice that tangent line. I could try to zoom in, and it's only going to touch that parabola at that point. So it's not a secant line, it is a official tangent line. So there's evidence, visual evidence, that we found the correct slope at -4, and then we have the correct tangent line. All right, if you want to pause it and take a little break, this is going to be a little longer video. So come on back in a minute or two. All right, so let's take a look at this one. What if I want to find the rate of change of a different function? Notice rate of change. This is basically the same thing as saying instantaneous rate of change. How do I know it's instantaneous rate versus average rate? Well, look at part A. They give me a single point. This is one point, and I want to find the rate of change at a point. I can't do regular slope, so I have to do the limit definition of the derivative. So I'm going to take the limit as x goes to c. Well, in this case, c is 2. And again, I like to write this out. A lot of students end up skipping this, but my first part of the slope is just regular x and f of x. The second part of the slope is the change at c. So what if I take f of x and now evaluate it when its c is at 2? So I'm going to put 2 here, and its output is f of 2. Well, I need to do a little side work. I need to just take the original function and figure out what is f of 2. So I'm going to plug in 2. Simplify, that's 4 minus 10. We get negative 6. So now I know f of 2 is equal to negative 6. And let's substitute in what we know. I know the limit as x goes to 2. And now notice, f of x. Well, wait a minute. Don't we know what f of x is? We're going to replace f of x with what it's equal to. It's the entire function. And then we're going to subtract that from whatever f of 2 was. And that's what we just found right here, negative 6. Notice I'm going to just put parentheses because that's pretty important. And then we're going to divide by x minus 2, because minus 2 is the c. So now we're just looking at evaluating the limit. Well, we've got some hopefully familiar pieces going on. I'm going to do a little bit of algebra. Oops, let me do correct algebra. I have a trinomial up top, and that trinomial can actually factor. So notice, by the way, see how I keep writing the limit as x goes to 2? If you don't have that, it's changing the context of the problem. So you need to make sure that you write that limit as x goes to 2 every single time until we use the limit. So pay really careful attention to my notation. All right, what did I do? I factored the top. Factors of 6 that add up to negative 5 are negative 2 and 3. And notice, got a common factor on top and on bottom. So when that reduces out, now I have the limit as x goes to 2 of just the function x minus 3. I should have addressed this. Why didn't I just plug in 2 right away up here? Because 2 minus 2 in the denominator would give me 0, and that doesn't work. We can't evaluate the limit that way. So we had to factor. Now, watch, I wrote the limit as x goes to 2 for every step until right here. I'm going to actually use that. I'm going to plug in 2 to the limit, the equation, and my answer ends up being negative 1. So, what did we just find? We just found the derivative. Watch my notation. F prime when x is 2, the slope is negative 1. So this is saying this is the slope when x is 2 of the function is negative 1. All right. We're going to take the exact same problem, but now we're going to use it for any value. And you'll see the benefit to doing this. It's not always easy, though, so you got to be careful. The function is x squared minus 5x. So I'm going to scroll down here. And we know our function. And then we want to find it when x is equal to c. So when we have any value, well, that's just taking the limit as x goes to c without putting a number in there. We're going to do the same thing. We're going to take the limit of f of x minus f of c over x minus c. So nothing new, it's still the slope formula. But now I'm going to plug in what I know, and this is where you got to be careful and really pay attention to how things are being set up. Okay, so let's think about what we know. F of c, that's the function. That's going to go right here. X squared minus 5x. And then we're going to subtract whatever f of c is. Well, how did we find that? We plugged in c here and here. So f of c is c squared minus 5c. I just plugged c into the function to get its output. And then on the bottom, we still have x minus regular c. So this is where it gets really weird and confusing. All right, so pay special attention. If you have to pause it a couple times to get caught up, please do so. Well, first thing I'm going to do is I'm going to distribute this negative. So it'll be negative c squared, and then distribute to give me positive 5c. And then I have a factor of x minus c on bottom. Well, I can't plug c into x, because I would get c minus c, which is 0. So I have to see, is there a factor of x minus c from this mess up here that I could reduce out? And it just has some tricky algebra, so please bear with me. Notice I have x squared and c squared. I'm going to group those together. This is just rearranging subtraction or addition. Then I've got 5x plus 5c. So I basically just switched the spots. Well, if you notice something, these values can be factored. I'm going to do, remember my factor by grouping? I'm going to group those together and factor out those terms. This goes back to Algebra 2, factor by grouping. So from the first factor, this is actually a difference of squares. Remember, x squared minus 4 would give me x minus 2x plus 2. Well, this is just the same thing. I get x plus c, x minus c. And then I've got a I'm going to pull out a -5 from each one of these. So the negative's going to take away from each of those. So I'll have a -5. And if I do that, I'll have a positive x left over and a minus c left over. Notice what happens. Minus c's all reduce out. Now notice this is a subtraction, so this side and this side have to have a common factor to reduce out. And then what's left over is up top, I got x plus c, and then I have a -5 left over. So now what happens if I want to plug x equals c into the function? I can plug c right in there, the spot where x is. So I get x or c plus c minus 5, and that gives me 2c minus 5. And this is the equation of the derivative for any constant f of c. So why is that beneficial? Well, what if c was 10? Instead of doing all this work every time, I could plug 10 in here. 10 times 2 is 20. 20 minus 5 is 15. The slope is 15 when c is 10. What if I went back to the very first problem we just had, part A? What if c was 2? Didn't our answer give us -1? Let's plug in here. If c was 2, 2 times 2 is 4. 4 minus 5 is -1. So this is a really fast, not fast, but it's a really convenient way to do first. All right, next example. All right, so let's get into a little bit of context. If you're taking physics at any point, you're going to really talk about motion. And that's what this is going to look at. If you would like to, you hit pause, and we can go through and kind of read this. But I'm going to just skim over the important parts. If we apply context and I look at the average rate of change, that's velocity. Velocity is the average rate of change, is how things move. So we have to first talk about something called rectilinear motion, which is basically motion along a straight line. And we got to talk about the initial position, which is usually given as s or f of t. Notice there's no tick mark there. There's no f prime. So this is just position. Well, we're going to look at and say, if I know the function, I can take the derivative and I can get the average rate of change, or actually the instantaneous rate of change at a point, which is velocity. So if t is the time traveled, s is the signed distance from the object, basically s is the position. Well, to figure out how fast it's going at a single spot, we can take the derivative to find the instantaneous velocity. So we're going to just kind of briefly go over this. Here's an example that has some context. Finding the average velocity. Notice average, that's like the Iroc. That's your just regular slope from Algebra 1. So if you see average velocity, it's regular slope. Change in y's over change in x's. So here's some context about a bridge in Colorado. It's 1,900 feet wide, and it's the 890 feet above the river. So it's really high and really long. But they give us the fact that if a rock falls from the roadway, it has a position function, s is position, or we could call it f of t, function with respect to time. And here's the function, it's 16t squared. That gives us the distance that the rock will fall in feet after t seconds. And then they give us the interval. They say when x is 0, notice x is 0, what's the output? Well, if I plug 0 into the function, 0 squared times 16 is 0. And then they say, well, we're going to end at the spot where the rock hits the water, which is 7.458 seconds. Okay, so that's my other input. That's the x value. And then the change in y's is when you plug 7.45 into 16 squared. Well, if I do that, I get 890 feet. Look at change in y's over change in x's. That gives me my average velocity. And look at the units. It's feet squared. It's moving at this rate over the average course from these almost 7.5 seconds. The average speed is 119.335 feet per second. Quick little note, notice when they round, anytime you have a decimal, you want to round to at least 3 decimals. And we'll talk more about that. Now, this is the average velocity. It's just regular slope over 2 points. That's Algebra 1. You could have done this 4 years ago. What about velocity? We're going to take the same example, and I definitely want you to write this one. I don't think we're going to do part C, or B, sorry. We're going to do A and C, and then we'll get our answer to C, and we'll come back and see how quick B is. So, use the definition of instantaneous velocity. Isn't that the same thing as derivative? So, instantaneous velocity is the derivative, which, look at, our position function was 16t squared from the last slide. Well, to find the derivative, that's finding f prime of t. Some kids don't like putting t, they like to put x, whatever you want. And this is at time 0, or the initial time. Another way of thinking of it is c is equal to 1. So we're basically doing the exact same thing we just did, but now we have context to our answer and the problem. So let's go ahead and do this. If we know the position function, and I want to find the instantaneous slope at 1 second. How fast is the rock falling at 1 second? All right, well, I'm going to take my limit. Oops. Now this is where, look at my habit, I put x. Well, in this case, we don't use x because the input variable is t. So now I want to do this when t is moving closer and closer to 1 second. And what are we doing? We're taking the original given function, f of t, minus the function when t is equal to 1. So there's my change in y's over my change in x's. When t goes in, t comes out, f of t comes out. When 1 goes in, f of 1 goes out. Well, now we just have to evaluate. The only thing I don't know is f of 1, but I can find that. I do know what f of t is. Right? F of t is the position function. They gave it to me here. I ended up just rewriting it. You don't have to show any work for this, but if you plug in 1, you could do that in your head. You know that after 1 second, we are 16 feet below the bridge, or it's falling at 16 feet. So f of 1 is equal to 16. And now let's evaluate. I almost wrote x again, but we got to remember t is the variable. So what is f of t? Well, that's the function that was given, 16t squared, minus what is f of 1? That's 16. And then that's still divided by t minus 1. I like to put that in parentheses because most likely you can see I can't just plug 1 in. I'll get 0 in the bottom. So we're going to have to do some type of algebra. And to be honest, we're going to start with pretty friendly algebra where it's just factoring. So let me just match my highlighting pieces up so you can follow that if you're looking back. All right, well, what do we have to do up top? We can factor this. I want to try to get a t minus 1 factor away from this. And what I'm going to do first is just say, you know what? Isn't there a 16 that we can pull away from there? So I'm factoring 16 away from each. So then 16 is a multiplier. And I've got t squared minus 1. There's a difference of squares again. So factoring that, we get t minus 1 times t plus 1. And you can kind of see why people use x's instead of t's, because especially my writing, it gets kind of sloppy. Well, look at that. By factoring the difference of squares, a t minus 1 reduces out. And what's left over is a limit that we can actually evaluate by plugging in 1. Don't forget the 16, though. We got t plus 1. So if I plug in 1, I get 16, 1 plus 1, that's 2, and I get 32. Now, context, what was this? We did our change, this is slope, right? This is our equation for slope. We did the change in feet over the change in time, which is seconds. So my units would be feet per second. And what is this? This is f prime at 1. That's the derivative at 1, which another way to think of this is the velocity. Exactly at t equals 1 second. So how fast is this rock falling at 1 second? It is going 32 feet per second. Okay, so that was part A. Yeah, it's a lot of work. You're going to have to do a lot of work for the next couple days. But part A said find the velocity at 1 second. We're going to skip part B and we're going to do part C. What about for any second? Instead of t of 0, I'm going to call it c because that's friendlier to use. We're going to use the same function. So let's take a look at this. If I know my position function and I want to find any value, let's say as t approaches c. So what do we have? We've got our limit definition of the derivative. Now we're approaching c, and I'm going to do f of t minus f of c, right? Because that's our new point of interest. So if c goes into the function of f of c, that means there is an input of c. And on the bottom, we're subtracting our x's. So change in x's, change in y's. Well, we already know that's an arrow. We already know what f of t is. F of t was 16t squared. And what happens when I plug c into that? I get, instead of a t, it becomes a c. And then on the bottom, we still have t minus c. And notice here, you're going to notice a lot of similarities in the work we do. I can't plug in c into t because c minus c is 0. That's an indeterminate form. And we know that there's a factor of 16 here left over, right? So if I factor that out, what's left over is t minus c squared. And you might not recognize it right away, but that's that same difference of squares right here. How did I get t squared minus c squared? Well, we had a factor. And how did I get the t? Well, oops, I got t times t. So there's a t and a t, but how did I get the minus c? That had to come from a plus c and a minus c. And notice the benefit to doing that. When I factor that out, what happens? the t minus c factors go away, and now I'm left with a limit as t goes to c of this new function. Well, I'm going to save some time, and I'm going to say, let's plug t equals c. Let's plug c in for t. So I get 16. Here's t getting closer to c, so c goes in. And then I get c plus c, which is really 2c. 16 times 2 is 32c. Whoa, wait a minute. What did we just find? We found the derivative at any value c. C stands for a constant, which means I can plug in any number. And again, what is that? That's the velocity. That's the equation for velocity. So what if c was 1? What if I plug in 1? I get 32 feet per second squared. Wait a minute. Isn't that all the work that we did right here? So hopefully you're seeing, I see why you didn't want to do b first. Because b would be all this work again, but instead of f of 1, it would be f of 7.4. So now that we know our general equation, now I'm going to do b. Part B says, what if c is 7.4 seconds? I'm not going to do all that limit work stuff again. I'm going to take my equation for the derivative, 32c, and just plug in 7.4. So 32 times 7.4 gives me 236.8. I think it was feet. I got to double check. I'm pretty sure it was feet per second. It might have been meters, but I'm almost positive it's feet. So what does that mean? How fast is the rock falling? This is the velocity at 7.4 seconds. All right, last problem. I'd like you to try this on your own. It's a little tricky, but find the derivative of f of x when x is equal to 2. Another way to state that is we got to find f prime of c. So I'm going to take the limit as x approaches 2. Notice that's, how do I know it's 2? They told me 2 ways. They told me here, and the input is 2. And then I'm going to just set it up. F of x minus f of c, but this time c is 2, and x minus 2. So again, remember, that's your slope problem. Now, you have to write the limit as x goes to 2. If you're not writing that, if you're skipping steps, you're not going to receive full credit. And that's one of the hardest things to learn in calculus. All right, so what do we know? F of c is just the equation. That entire thing is going to go right here. And then we're subtracting whatever f of 2 is. Well, that's just the point. So I'm going to plug in 2 everywhere I see an x. Well, 2 squared is 4. 4 times 2 is 8. And then 3 times 2 is 6. So minus 6 minus 2. That's going to give me 0. F of 2 is equal to 0. And that's all over my equation. Now, notice right away, I can't just plug in 2 because I get 0 on the bottom. That's going to happen every time. So what I'm looking for then is, can I do something to the top to factor it and see, is this factorable? Now, I'm not going to rewrite this again because the minus 0 doesn't change it, but I'm going to use my factoring, and I consider this side work. I need a bigger box. Okay, see, wasn't that easy? I just plugged in my trinomial, multiplied the corners. I'm looking for factors of negative 4x squared that add up to give me the middle term. I get negative 4x and 1, and then I'm pulling out common factors, top and bottom. When you do this, it is expected that you are very comfortable with factoring, so we don't go over those skills unless you have individual questions. So we factor the top. this part right here factored out, and notice the benefit. What happened? We had a common factor reduce out. And now I can evaluate the limit exactly at 2. So we can plug this in. Notice, as soon as I plug 2 in, I no longer write the limit. So what did I just find? I found the derivative, or the slope, or the velocity, if you want to think of it, at 2. Now, the last part is to write the equation of the tangent line. And I'm going to use our function notation. I need the slope. This is m, so this is my point slope equation. Y minus y1 equals m times x minus x1. Here's the slope. We just found that. And then I need the point. I need the point at 2, that's x is 2, and I need its output, which we already know from above. So you already have all the pieces of information you need. When 2 went into the function, 0 came out. When we found the derivative, we got a 5 for the slope of the tangent line when x is equal to 2. And then the 0 doesn't go anywhere, distribute. Here's the equation of the tangent line. And if you're not positive on that, graph the tangent line and graph the original function and you'll see the graph. Okay, quick recap. What did we just learn? We learned the limit definition of the tangent line is the slope of the tangent line as x approaches c, and we use this every time. Remember, the derivative is the instantaneous rate of change. It's also the velocity if there's context to the problem, and it's the slope of the tangent line. Homework tonight is in your textbook, section 2.1, and here are the page numbers. I will post this on Schoology, and I'll even do a screenshot of the problems so you can see them. Whew, have a great day. I'll be, on Monday, I'll be live in person with you again, and I'll have office hours. We can go over this if you're struggling. Have a great day.